Hey everyone, welcome to yet another episode of this video series on Joshua Bloch's Effective Java, where I try and expound and make sense of the items that he has enumerated in this book. And without further ado, let's get started with the introduction, because I sort of anticipate that this item in particular is going to be a long one, because there are a lot of, I'd say, ancillary points that we need to discuss to make sense of the crux of this item and the argument that Joshua Bloch is putting forward. So, as per usual, I'm going to go through the same introduction that I go through in every single video in the series. So if you've been following along, please do skip this bit to save your time. The proviso goes like this, which I'm kind of sick of repeating, but I feel like I kind of have to repeat it for, let's say, due diligence or just to be ethical about this whole thing. This is not a tutorial. I certainly am not a teacher, nor am I an expert. So, take what I say with a grain of salt. Don't think of this as any other tutorial on YouTube where what I say is, in some sense, gospel's truth. I don't think every single tutorial on YouTube is like that, but there are some tutorials where certainly, they're good quality, they come from an expert in the field, and you can trust what they're saying. Don't trust what I say. I'm pretty sure I'm gonna butcher a lot of things in this item, and in some sense, hopefully, try my best to do it as accurately as possible. Not splitting the bullshit, but getting to the points in the item. There certainly are going to be unintentional mistakes that I make. I'd like to think of this as the blind leading the blind. I'm as blind as you are, perhaps even more. This is merely, or not merely, this is a exploratory disquisition. I'm trying to make sense of this collectively, using different forums like Stack Overflow. Whenever I come across something that I don't understand, I'd post a question on Stack Overflow, and I'd really appreciate it if I do make any mistakes, which I think I inevitably will, please point them out in the comment section down below. Not just for my sake, but even for other people that are watching these videos. I really don't want to mislead people in any way. And given that this is a programming video series, it only makes sense to have all the code that I use on GitHub publicly available. I'll leave a link down below, not just to my GitHub account, but also Joshua Bloch's sort of official public repository that he's published and put out all the code used in the book. And saying all that, let's get started on item number 7, which states eliminate obsolete object references. And this again is from chapter 2, creating and destroying objects. So something I've been trying to do in these videos is, before we even get to the content of the item, to try and expand on and try and understand basically what the words used in the title itself are. So object references. What in the world are object references? This diagram or this image pretty much puts it quite simply. An object reference is merely a pointer, or not merely, it's probably good to conceptualize it as a pointer. So we have objects in the heap memory. So the memory is subdivided into different segments by the JVM. There's a heap, there's a stack, and generally, leaving aside the stack and the heap, what a object reference is a memory address. The pointer points to a memory address of a particular object in the heap. And adding on to that, in this image, if we take something like an object array, let's say, an array itself is a reference to another object. What I mean by that is an array can exist in the heap, and there's a pointer or a memory address that points to that array. But the items in the array itself are pointing to other objects within the heap. So in some sense, you can, I guess, think of it this way, the way they've shown in this diagram, where the array contains references itself, and it could also contain a null. So if you null out an array, which we're going to see some nulling out in this item, then it's not going to point to anything. So in Java, what happens when we use the new keyword is we reserve a location in memory. When we instantiate a class, the constructor of that class, and all classes have a constructor, creates a reference to an object. And a reference I said it's like a pointer, but another way of thinking about it is that it's information regarding the location of the object in memory. So what we see here is an example of that, where we're creating this object array, a primitive array, and we're instantiating it, in this case with a primitive type. So just repeating the point, item 7 states again, eliminate obsolete object references. So unlike a language like, let's say, C++, Java does automatic garbage collection. What is garbage collection? It's simply put, memory management. When we do allocate resources to a certain object, we make sure that once that object is no longer in use, we clear it out. We let that memory go we free out resources so that that resource can be used for something else. And there are different algorithms used in garbage collection. In fact, I'll leave some links down below on some videos by Gaurav Sen, I believe. I think that's his surname, but he does the system design videos on YouTube. Really good, superlative content, and he does do a bit of explaining of how these algorithms work, specifically apropos JVM. So, of course, because Java does automatic garbage collection, as I said, unlike a language like C++, we could make the wrong assumption. When I mean we, I mean a programmer could make the wrong assumption that we don't have to think about memory management at all. And that's why in the beginning of this item, Joshua Bloch states, when it comes to garbage collection, it seems almost like magic when you first experience it, and therefore it can easily lead to the impression that you don't have to think about memory management. But this isn't quite true. I had to take off my cardigan because it was getting really hot in this room. Summer's coming in Melbourne, yay. So he keeps going, consider the following simple stack implementation. I've got the stack implementation right here. However, before we get to the code and do a deep dive, I kind of again want to backtrack a bit and discuss some of the terms. So we discussed what object references are, and then I want to discuss what's a obsolete reference. An obsolete reference is a reference that will not be dereferenced again. It's unintentionally retaining an object. Now, this term here, dereferencing or dereferenced again, this can be quite confusing because dereference does not mean that you get rid of the reference. Not at all. What dereferencing in fact means is when we do refer to an object, in our code somewhere down the line, once we do create the reference, we may refer to it again. We may get the value that the reference is pointing to. That process is called dereferencing. And if we don't dereference an object, there's no use of keeping an object in memory. So we're unintentionally just leaving an object there, allocating resources, making our application inefficient. That shouldn't be done. So the solution is quite simple. In fact, it's simply to null out references once they become obsolete. And we sometimes have to do this explicitly on our code, despite Java doing memory management or garbage collection. So to have a bit of a more formal and clear definition by my favorite Java programming website, Bile Dung, dereferencing means the action of accessing an object's features through a reference. And one way to prevent obsolete object references is by narrow scoping. And what's narrow scoping? That's something what you would see in a for loop. In a for loop, we have the int, you declared int I, for instance, that variable is within the scope of that for loop. So narrow scoping, that's an example. Another example would be trying not to declare global variables in a class. Rather, declare the variables within a function, within a method, and keep it localized to that specific method. And that helps with eliminating obsolete object references because we sort of know what the scope of a variable is in our code base. And then in the item, he keeps going, and this is the code base for the stack class. And then he asks, can you spot the memory leak? Saying that before we get to the item and try and visualize what the memory leak is, let's take a look at the code base and the code base of this stack implementation, a really simple stack implementation that Joshua Bloch has used here as an example to illustrate his point. So I'm pretty much going to go through this code line by line, despite it being a bit long, because I think that's the best way to understand this. We have a simple class called stack. We have a object array of elements and another private, the object array is also private, but also another private variable called size of primitive type integer of int, sorry. And then this constant here is what initially defines the initial stack capacity. So when the stack class is instantiated, of course, the constructor is called. And in the client over here, I am instantiating the class, line number 57. So when the constructor is called, a new object array is initialized. So this array we defined here, elements, that this new object is passed to that variable. And when the new object array is initialized, its default capacity is, I've made a mistake here, it's not 26, it's 16. And that's assigned to the variable elements. So this variable in line number 10 will hold I'm pointing to the code as if you can see where I'm pointing at. That's so funny. Anyway, this object array will hold a reference, or elements will hold a reference to this new object that was created and that's in the heap. And then we have a method called push. And what that does is, as you'd expect from a stack, you can push new elements or new objects onto the stack, or in this case, the elements array. But in that method, we have another method that we call ensure capacity. Ensure capacity just ensures that there's space for at least one more element, roughly. And if not, it'll just double the capacity each time the array needs to grow, because we want the stack to be dynamic. You can see here it's creating a copy of elements and passing it to elements. And the more we keep adding onto the stack, the more the array grows. So it doubles in size, let's say. Now we get to the point. This pop method is what's pertinent to our item and where we see memory leak take place. So we have this object method. Sorry, we have this pop method, and we don't. Here in this method, garbage collection doesn't take place, and that's why we need to be aware of that. So firstly, if the size is equal to 0, we're just going to throw an empty stack exception, and we can't add stuff into an empty stack. And here we see that when we pop the object of the array, or when we return the object that's in the array, where we reduce the size with this counter. So this was the variable we declared here in line number 11. And when we reduce that, oh, sorry, I didn't say that. In fact, in the push method, whenever we push a new item onto the array, we also increase the count on that variable. And when we pop it, we reduce it. Kind of makes sense. But what happens here, though, is whenever we pop an object from the stack, or when we take an object out from this array, an object is still unintentionally retained here despite the client of this class having no use of those objects. And that's where the memory leak takes place. And the proper way to do this, and again, this bit of code here, line number 28 to 33, I will illustrate that in this diagram more visually. It'll make a lot more sense. Whoops, that was a mistake. Getting back to this. But this is not the right way to do it, because what's happening here is a memory leak. The proper way to do it would be like this. I'm going to comment out the wrong way. It would still be where we are checking if the stack is empty. The stack can't be empty. And then we are, in fact, assigning this value onto a new variable we're going to create called result. So whatever the elements array returns after we reduce the size, we're going to assign that value to result, and then simply we null out that location on the array. And that's where the elimination of the obsolete reference takes place. And we return the result afterwards. So we assign it to result and return the result, but we ensure that that element in the array, that index that we return, that it's nulled out. Because when it's nulled out, what happens is something like what we see here. it's clear that it's not obsolete, that it's not pointing at something and taking up memory resources. And really, if you run this code, there really isn't a use in running the code, but this is kind of what you'd see. You just print out the array, or the stack in this case. You can ignore this empty stack exception. The reason for that is because we're pretty much pushing everything into the stack and then popping everything off the stack. And then you would, at one point, as we go through it, expect this exception to be thrown here, which is, wait, I just missed it. Right here. Because what happens is we keep popping the stack. At one point, the stack gets empty. So this is kind of expected, this error here. So now, before I read out what Joshua Bloch has explained here, let's take a look at this diagram and visualize it. So here we have that elements array that I spoke about before. So that's the array right here, like the object array that we defined. That's what I've illustrated or represented here. And let's say the objects are integers, and we're adding 1, 2, 3, 4, 5, 6. I don't know why I put a 0 in front. Let's just think of it as 1, 2, 3, 4, 5, 6. And then this is being added by the push method here. But then, for some reason, we also pop some of it, and we pop 3 items from the array. Now, what happens here is, if we don't null out the references the way we've done here, these things are still going to exist in the array. However, for the purpose of the stack class, the client will never use these elements, these objects. They'll just exist in memory, making them obsolete, and more importantly, making it a memory leak because it's taking up resources that could be used for something else. And that's the problem here if you don't null that out. So the right way to do it is to treat this array in this way, where the way we've done it in the proper pop method, every time we return whatever is in the index of this array, we also ensure that it's nulled out. And that way that reference is eliminated. The obsolete reference is eliminated. I hope that makes sense. I know I'm repeating the same point, but repetition is important to make sense of this. And on the note of repeating, I'm going to read out what Joshua Bloch has said about this particular class in the book. He goes like this. There's nothing obviously wrong with this program. You could test it exhaustively and it would pass every test with flying colors. But there's a problem lurking. Ooh, indeed. Loosely speaking, the program has a memory leak, which can silently manifest as reduced performance due to the increased garbage collect activity or increased memory footprint. What can I pronounce that word? So that's the increased memory footprint is what I explained here. That these 3, let's say for this example, these 3 indexes taking up space in the heap. He keeps going. If a stack grows and then shrinks, the objects that were popped off the stack will not be garbage collected, even if the program using the stack has no more references to them. So that is what we saw in the other method, when it's wrong, the way it shouldn't be done. There's a nulling out here. This is because the stack maintains obsolete references to these objects. An obsolete reference is simply a reference that will never be dereferenced again, so never be used by the program again. In this case, any references outside of the active portion of the element array are obsolete. It's important to understand what he means by the active portion. The active portion really is the portion of the array that the client would care about or use, the client of this class. So in this example, the active portion really is index 0, 1, and 2, not this bit here, which is why they should be nulled out. The active portion consists of the elements whose index is less than size. Yes, so this size here is what holds the size of the stack. And then he sort of concludes that point by stating, memory leaks in garbage collected languages like Java, more properly known as unintentional object retentions, are insidious. If an object reference is unintentionally retained, not only is that object excluded from garbage collection, but so too are any object objects referenced by that object, and so on. It's an interesting point there because I've had a conversation with a C++ engineer or developer in my company, and he kind of made the point, that's kind of the trade-off we make in programming. The more we sort of give control to the virtual machine, in this case a JVM, the less we know what's going on kind of behind the scenes, under the hood. The more abstractions on abstractions we build, the less of an understanding we have as to what's going on in our program. Which is why, for instance, when it comes to using packages, sometimes it can be dangerous and, to use Joshua Bloch's term, insidious, because we don't have a really good, thorough, deep understanding of what's happening, let's say, at a memory management level. So as a good programmer, I guess it's important to be kind of prudent and careful about that, and be judicious as to how we write our code. Anyway, before I get carried away philosophizing about programming, let's get back to the point here. And the item he states then, the fix for this sort of problem is simple: null out references once they become obsolete. That's what I've shown here. I already showed the solution in the code itself. An added benefit of nulling out obsolete references is that if they are subsequently dereferenced by mistake, the program will immediately fail with the null pointer exception, rather than quietly doing the wrong thing. It is always beneficial to detect programming errors as quickly as possible. Now, I don't know how in this class someone could dereference parts of this array that theoretically should not be accessed in the stack class, but it's possible. If the array was public, let's say, by mistake, and it would be a theoretical mistake if after the size of the stack changes, let's say the size of the stack was 3 and we only had 0, 1, 2, and 3, and we still give access to the client to 4 and 5. That would be a mistake. But when we null it out, the error is explicit and clear because the program will throw a null pointer exception. But interestingly, then he also makes the provision that nulling out object references should be the exception rather than the norm. So technically, this thing, what we've done here, shouldn't always be done. There are better ways to handle this or eliminate obsolete references than just nulling out elements in this area, let's say in this example. The best way to eliminate an obsolete reference is to let the variable that contain the reference fall out of scope. This occurs naturally if you define each variable in the narrowest possible scope. And this is kind of what I meant by narrow scoping. Is one way that allows eliminating obsolete object references. And I did explain what narrow scoping is. It's ensuring that when we define a variable and we declare a variable, it's in the narrowest possible scope in our source code. But if he says nulling out shouldn't be the norm, why in this example he's given in the stack class, why are we nulling out these references? Why not use narrow scoping as he suggested, which he says should be the norm? To put it simply, he says it's because the stack class manages its own memory. We see that here. We see that as to what's going on here, where we're managing the memory apropos this array here. The storage pool consists of the elements of the elements array. That's a bit confusing, I know, but the elements inside this array. So each individual element, which he's added here are the object references, not the objects themselves. So these are references themselves. And then the elements in the active portion of the array, as defined earlier, are allocated, and those in the remainder of the array are free. So that's the active portion, that's allocated, and these are made free. The garbage collector has no way of knowing this. To the garbage collector, all of the object references in the elements array are equally valid. Correct, because the garbage collector doesn't know what the purpose of this stack class is. The garbage collector isn't that intelligent. Hopefully, in the future it would be. Only the programmer, or GitHub Copilot, perhaps, knows that the inactive portion of the array is unimportant. The programmer effectively communicates this fact to the garbage collector by manually nulling out array elements as soon as they become part of the inactive portion. That's correct, that's what we've done here. And then, just to conclude that point, Joshua Bloch states, generally speaking, Whenever a class manages its own memory, the programmer should be alert for memory leaks. So what other examples can we think of when it comes to memory leaks, apropos Java and JVM? Another example that he's given here is memory leaks that we would see in, sorry, I shouldn't say apropos Java and JVM. This is just commonly in programming, in, let's say, OOP programming in general. These examples he's laid out or laid down could lead to potential memory leaks. And the first one is given is in caches. It's quite common to see memory leaks in caches because, of course, what happens a lot in a cache is we cache data. And when we do cache data, when we cache objects, there's a high possibility, if we don't do it in a smart, thought out way, that it can lead to obsolete object references, because once an object reference is put in a cache, it can be left there long after it stops being relevant, thus being obsolete. And the solution for this problem of memory leaks in caches that Joshua Bloch has suggested is using weak hash maps. And when I said in the beginning of the item that there are some ancillary points, some concepts we need to understand to really get to the crux of this item, this is what I meant. I've never used a weak hash map in my life. Therefore, I had to do a bit of reading and studying as to what weak hash maps are. So Joshua Bloch states, before I get to what a weak hash map is and before I go through the code, which I've got here, I've got a weak hash map demo. Joshua Bloch states, if you're lucky enough to implement a cache for which an entry is relevant exactly so long as there are references to its key outside of the cache, represent the cache as a weak hash map. Entries will be removed automatically after they become obsolete. So conceptually, that sort of makes sense, doesn't it? Because the reason we have a cache is for quick access of data, of objects. And the key in a cache, we got to make sure that whatever data that's in the cache, that the keys are relevant outside of the data structure in the cache. In this case, it could be a hash map. So that ensures that we don't have obsolete object references. And he keeps going that, remember that weak hash map is useful only if the desired lifetime of cache entries is determined by external references to the key, not the value. Okay, now let's understand what a weak hash map is. Firstly, before we get to the code, let's get through some definitions. It's important to get a theoretical understanding, a conceptual understanding of what this is. And one of the best definitions, as per usual, that I found is by Dang's blog. It's this blog. Oh no, that's on Profilers. It's this blog post here, a guide to weak hash map in Java. And he states, simply put, the weak hash map is a hash table based implementation of the map interface with keys that are of a weak reference type. And now we have another term here. What are weak references? For that, we'll open up the best explanation that I found is this Stack Overflow answer. And in fact, this user says that it's by Ethan Nicholas, but the name of this user is Michael Myers. And a weak reference, simply put, is a reference that isn't strong enough to force an object to remain in memory. Weak references allow you to leverage the garbage collector's ability to determine the reachability for you so you don't have to do it yourself. But also in this article by Dang, he's given some pretty good definitions where he discerns between strong, soft, and weak references. So a strong reference is what would normally be when we declare a variable like this, let's say. That's a strong reference. And this is the most common type, and it's not eligible for garbage collection. A soft reference is eligible for garbage collection, but only when the JVM needs more memory. It absolutely needs more memory. In fact, he's made that point here. It's kind of like a last resort kind of thing. But a weak reference is not that. A weak reference doesn't, the garbage collector is given volition where it can sort of eagerly garbage collect. It won't wait until it needs more memory. It'll just use it up if required. And that's where using a weak reference in the context of a cache helps us to eliminate obsolete object references. So in any case, that's another definition of a weak reference. There's also this article that I read, which is quite good. I think it gave a pretty good practical and sort of applicative explanation of what, well, the title of the article is practical uses of weak references by this user, Philosophical Geek, or I guess Ben Watson. I'll leave a link to this down below too, where he goes through, well, he starts off the article by saying that you rarely use weak references, but if you do use them, it'll mostly be for framework building or when it comes to something at more of the memory management level. And Java programmers, at least day-to-day Java programmers like myself, don't really do a lot of memory management. But this is a good article to read, just for learning. So back to the weak hash map definition, which uses weak reference type, by the way. Baldan continues, an entry in a weak hash map will automatically be removed when its key is no longer in ordinary use, meaning that there is no single reference that point to that key. When the garbage, so what this bit means here is in the key value pairs in the hash map, if the key isn't being used anywhere outside of the data structure, outside of the cache, that means that there's no single reference. Therefore, it just could be removed automatically, and having a weak reference helps. When the garbage collection process discards a key, its entry is effectively removed from the map, so this class behaves somewhat differently from other map implementations, because normal map implementations would have a strong reference, and you can't just let the garbage collector just do garbage collection as it wishes, eagerly. It's a bit more tighter and a bit more stricter. I just realized that I didn't go through this canonicalized mapping bit. That is in fact from the Oracle docs that defines what weak references are. So the docs state weak reference objects which do not prevent their reference from being made finalizable, finalized, and then reclaimed. Weak references are most often used to implement canonicalizing mappings. What does that mean? So this is another really good blog post I read on weak references. Sorry, I had to find the blog post here. And the title of the blog post is itself canonicalized mappings. I'll leave a link to that down below. I'm not going to go through the whole thing, but the definition is by Tom Rosen and Ian Lowe. A canonicalized mapping is where you keep one instance of the object in question in memory and all other lookup that particular instance via pointers or some such mechanism. The short answer is that weak reference objects can be used to create pointers to objects in your system while still allowing those objects to be reclaimed by the garbage collector once they pass out of scope. That kind of makes sense. I mean, it makes sense in the sense of I can see why theoretically a weak reference type can be used in a weak hash map to prevent memory leaks in a cache. I can see the reason. I'm going to be honest, I don't think I can still fully understand how to implement that in code, but at least conceptually, I can see the connection there. So now let's take a look at what a weak hash map is. So I created this class called the weak hash map demo. I kind of repurposed this example that was used on Baldang's blog. And firstly, this part really isn't a part of the weak hash map. I just want to show how to create a weak reference. That's how you do it. It's a generic type. You pass it of integer, and then you create the weak reference. Easy as that. And then when we made this prime reference null, initially we declared, then we make it null, this object will be garbage collected in the next GC cycle, as there is no other strong reference pointing to it. So when we create the weak reference, as you can see here, we are passing that object into the constructor of the weak reference class. And now this new object is of type weak reference. But that's just how to create weak references. Now let's get to the crux of this class. This is terrible coding. I should have put this somewhere else because this in no way is related to this class. But in any case, it's just for demonstration purposes. Here's how we create a weak hash map. So it's just like creating a normal hash map, really. We define the key and the value, the types of the key and the value. And ideally, we want a map implementation that allows garbage collection to automatically delete unused objects, correct? And because we ideally want that is the reason that we use a weak hash map. When a key of a big image object is not in use in application in any place, so that's the key for this object here. The unique image name in this case would be the key. This entry will automatically be deleted from memory. It's pretty cool, in fact, how this happens, and I'll show you this show this to you in code. So we have the weak reference map. Just ignore the other line of code I've used here. It's just a normal hash map I've used. I was just playing around with this, but what matters really is the map I've created here in line number 25. So for all intents and purposes, this hash map could be our cache, and we are putting a new big image object into that cache, into our hash map. We're also creating a key and putting that key to, and we're creating the key value pair here. And the image name, of course, is the object reference, which is the key. So if I run this code now, what you'll see is so what's this log here? Map does not contain image name. So that is terribly misleading. I just realized that log can be extremely confusing because the map is supposed to contain image name because they're putting it in line number 31, and we are nulling out any key here. So I'm going to run that again because that can be really confusing and kind of ruin the purpose of this demo. The map should contain image name. It should contain the key, because we haven't nulled it out and nothing has happened. And of course, the map will also contain big image, the big image object. Also, that's confusing. I should have prepared for this demo much better. I gotta get rid of that line because I'm adding it twice into the hash map. I don't know why I'm doing that. Anyway, in any case, I hope I'm making sense here. I profusely apologize because this is not a good demo. Hey, but as software engineers, we all know that whenever there's a demo, things break. So perhaps it is, ironically, a good demo because this is what a demo would actually look like. So initially, yes, it does contain the key, and it also does contain the value. And then what happens is we null out the key. That's all we're doing. We're not clearing anything out. And then we just run a garbage collection cycle. We force the JVM to write a GC cycle. And then almost magically, the bloody hash map is empty. And how is that? This wouldn't happen if it was a normal hash map with a strong reference. The way the hash map is empty, so this is the log here that you see, is in fact because this hash map is a weak hash map using weak reference type. So when the external reference to this key was nulled out, the object itself or the key value pair was garbage collected because it's not used. So that's the perfect implementation of a cache that'll prevent memory leaks. And then for this problem of memory leaks in caches, another solution that he's proposed is sort of using a least recently used cache eviction policy. But the implementation of it is a bit more different to kind of the conceptual understanding of what that policy is. And that can be done using a scheduled thread pool executor. And it could be, what this does is in the background on a separate thread, you can run tasks, scheduled tasks repeatedly, such as cache cleansing. And to understand what this is, what a scheduled thread pool executor does, I came across this article on Geeks for Geeks by a user called Samufo, and that's the user's pseudonym. And here's the implementation of that class. I think it's important to understand what this is doing, even though this isn't fully related to clearing caches. The way it'll work is like this. Anyway, by the way, all this code is on the GitHub repository, so please go take a look. And this kind of demonstrates how the schedule thread pool executor works. Initially, we create a object called thread pool. We create an instance of the schedule thread pool executor, and we pass the size, so how many threads, it's 2 threads in this case. And then we create 2 runnable tasks. So these tasks could be anything. It could even be something like the main let's say, the main thread that's running the program, and then in the background, clearing the cache in a given time. And afterwards, the first one will execute in 2 seconds and the second one in 5 seconds. It's simple as that. So if I run this method, you'll see the first one executed in 2 seconds and the other one executed a bit later, and then that a bit later. Sorry, that's the current time, I apologize. So that was in the execution. So that was the first task, and that was the second task. So I shouldn't have said evict cache for both tasks, because this could be, in fact, something else. It could be, I don't know, some main task, and then the second one, which we scheduled to run in 5 seconds, could be the cache eviction. So that's the implementation of that idea of a cache eviction policy using a scheduled thread pool executor. And to be, put it more formally and clearly, Joshua Bloch states, most commonly, the useful lifetime of cache entry is less well defined, with entries becoming less valuable over time. Under these circumstances, the cache should occasionally be cleansed of entries that have fallen into disuse. So that's where scheduling a task like this using the scheduled thread pool executor could come in handy, because we could time it. We could schedule a cache eviction in a given period of time. And then he even states that the linked hash map does this. So if you take a look at the docs for the linked hash map, there's a protected Boolean method called remove eldest entry. And that method, what that does is, in fact, it's an implementation of what Joshua Bloch has described here. It is clearing the linked hash map by clearing out the old entries. So it says it provides the implementer of this class with the opportunity to remove the eldest entry each time a new one is added. And then we get to the third way memory leaks could happen. So we've discussed how it could happen if classes manages their own memory. We've discussed how it could happen in caches. And the third way is, the third common way is, it could happen when it comes to listeners and other callbacks. When a client uses an API with a callback function. So firstly, what's a callback? So Rishabh Jindal from Geeks for Geeks states that a callback function is a function that is passed into another function as an argument and is expected to execute after some kind of event. I would also add, it's also an example of, how callbacks are implemented is an example of the observer pattern, where an object should subscribe to another object and listens to changes in events on runtime. And that's what a callback is. It's a function you can pass to be executed, contingent on an event during runtime. Even though I've used callbacks, obviously JavaScript uses, we use promises, but then a lot of JavaScript uses before promises use callbacks. And even in Java, we use callbacks. But I didn't initially get the understanding, or I didn't initially understand how it can work apropos weak references and how the garbage collection works when it comes to callbacks. So I did post a Stack Overflow question, and I got a really good answer by this user called Ingo Kegel. I'll leave a link to this question down below in the description. Go take a look. But using that user's answer, let's try and make sense of what... in fact, before I say that, I just want to say Joshua Bloch states, apropos this point, if you implement, when I mean apropos this point, that's when it comes to memory leaks with listeners and other callbacks, he states, if you implement an API where clients register callbacks but don't deregister them explicitly, they will accumulate unless you take some action. So what does that mean? What's the action we got to take? The action we got to take would be using a weak reference. And before we get to the code, I realized I should read out Ingo Kegel's answer here. He states, a client of the API has to keep a strong reference to the listener. That's how it says alive. Correct. So we can define the listener here as an interface. That's how we would normally do when implementing callbacks in Java. The API only holds a weak reference to the listener. To do that, so that it does not prevent, that's a typo there, I believe, so that it does not prevent the client from being garbage collected. So it allows garbage collection to take place if required. When the client is garbage collected, the listener is also garbage collected. That's a good thing, because we don't want the obsolete object, the listener object, to exist in memory and take up resources, and that's why a weak reference would help. Now, the implementation of that would be seen here. So this is the examples courtesy of Ingo Kegel, as I said. This is his code that I've repurposed to demonstrate this. So firstly, since Java doesn't support function pointers, this represents a callback. Effectively, it's a reference to the function which will be called. So because we don't use function pointers, we can use callbacks in Java. Function pointers can be used in C++, I believe. Don't quote me on that, because I'm not a C++ programmer. Why am I talking so fast and fumbling my words? Too much of coffee. So this callback demo represents the mock API that a user would use. Initially, I've defined the listener here. So this listener is of the type, the interface listener. And then we've got to initially register this listener. That's what the client would do. So the client of this API would do that a bit later, because the observer of this API has to use that method and register itself. This is a bit confusing. I should have maybe used a separate class and called it the client, but this callbacks demo class is the client of this API. Just keep in mind. So that client would have a strong reference. However, once the registering is done, the API itself will maintain a weak reference, because then what happens is, when this client at one point is garbage collected, so would the listener that it registers. And then we have this file listener method, which checks for the listener, which checks if it's registered, and then fires an event, which we've defined here, which runs some task. So that's kind of how it's used in the context of callbacks and listeners. And that's why using a weak reference would help with ensuring that there aren't any memory leaks when a client uses our API. And then to conclude, in the final paragraph, Joshua Bloch states, because memory leaks typically do not manifest themselves as obvious failures, they may remain present in a system for years. They're typically discovered only as a result of careful code inspection, or with the aid of a debugging tool known as a heap profiler. Heap profiler can also be called like a Java profiler. And that's a tool pretty much that monitors the bytecode, constructs, and operations at the JVM level. At a very low level, using a heap profiler, you could monitor your code and examine memory usage, how garbage collection takes place, if resources are being used wastefully, if there are memory leaks. All these things we discussed could be found through a tool like a Java profiler or a heap profiler. And again, Baldun's definition here. These code constructs and operations include object creation, iterative executions, including recursive calls, method executions, thread executions, and garbage collections. So it's kind of like a way of instrumenting your application and instrumenting your code, let's say, and really digging deep into it and examining it at a bytecode level. And that's obviously something that, I've never done it before in my life. Just on your IDE, you can't do that. You need a specific tool for that. Therefore, to end it, he states, it is very desirable to learn to anticipate problems like this before they occur and prevent them from happening. So that's why this point is great, because initially Joshua Bloch points out what the issue is. He kind of illustrates it, but then he also gives us 3 areas where this could potentially occur. We could kind of anticipate where memory leaks could occur when writing code, and the 3 places it could occur when it comes to having obsolete object references that we should eliminate is in classes that, just to reiterate the point, in classes that manage its own memory, in caches, and when it comes to callbacks and listeners. When you implement that in your API. That's it. That is the item number 7. Eliminate obsolete object references. As I did anticipate, it did go for over an hour because I did feel, even though the item isn't all that long or all that complicated, there were a few points like the implementation of the listeners and the callbacks, and then the weak references that I felt like we needed to dive in a bit more and understand. At least I needed to make sense of it. As I said, all the code that I used are on the GitHub repository, and the link to that is in the description down below. Please go take a look at the code. It'll make a lot more sense if you study the code assiduously instead of me kind of explaining it. Again, I'm trying my best to articulate myself while I'm also learning as I go. It's kind of how it works. You probably can see I'm struggling a lot with some of these concepts. But in any case, I sincerely do hope this video brought some value. You learned something from it. I shall see you in the next item. It is item number 8. We're still in chapter 2. And item number 8 is avoid finalizers and cleaners. And I'll get to that as soon as possible. In fact, I've already started writing the code for it. I'll see you in the next one. Cheers.